So first we shall come into the study of the Earth's internal structure as such. You see, Earth uh, millions of years ago, as such, Earth was formed by the corresponding cooling of, means the corresponding pulling down of the dust as well as gas under the effect of gravity. Later, as such, due to the fusion aspects, the temperature of the Earth during those times was very large, uh, which was also kept initiated due to the meteorites that come onto the surface of the Earth. Finally, what happened is that Earth cooled down. When it cooled down, the outermost layers of the Earth cooled down faster, and hence we had the outermost layers as a solid type. While the innermost layers, depending upon the pressure and temperature, some may be in liquid format or semi-solid format, liquid format, or even dense solid, depending upon what the corresponding pressure and temperature it is. So if you, as a general outlook, if you study the internal structure of the Earth, we can broadly classify the internal structure into three different layers. Okay, the crust, which is the outermost layer of the Earth. Then you have the mantle, and then finally the innermost part of the Earth is the core. Okay, the crust, or which we call it as the lithosphere, is the outermost part of the Earth's surface. Okay, in this corresponding figure here, you can see the crust. Now, the outermost crust part, you see there are oceans as well as continents. So, the crust, as such, some people to distinguish between the ocean as well as the continent, they say oceanic crust as well as a continental crust. Okay.
Excuse me, sir.
Yes.
Sir, are you showing the next slide, sir? After this earthquake seismology, I guess it's not visible to us. The next slides.
Okay. What about now?
No, sir, it is still the same.
Is it visible right
Uh,
now?
yes, sir. Now it is visible.
Okay. So, as such, the oceanic crust, the corresponding crust whose thickness is comparatively lesser under the oceans, and then we have something called the continental crust. So, as such, the thickness of the continental crust is more compared to that of the oceanic crust. Usually, an average of 40 kilometers is the thickness of the continental crust, while the oceanic crust is approximately has thickness of 5 kilometers. Okay, and you know the corresponding what you call it, the pressure at the surface of the Earth, it is 1 atm. Okay, 1 atm means 1 atmosphere pressure, and the temperature as such is maybe the density as such of the materials that constitute the crust, maybe it is 1.5 gram per centimeter cube. Okay, usually the oceanic crust is made up of basaltic rocks. Okay, and the continental crust is made up of granite rocks as such. I'm not telling everything, but generally, if you consider it, it is more composed of granite rocks for in the ocean, in the continent, and in the oceans it is basalt rocks. So as such, this is the thing, the outermost layer, or we call the another term for this is the lithosphere. Okay, the lithospheric part that consists of the oceanic crust and the continental crust. I think I'll show you a. Here is the different layers. So the last one here indicates the crust as such. So the continental crust, minimum 35 kilometers and a maximum of 90 kilometers, especially in the case of mountainous regions. Okay, you can have the thickness of the crust up till 90 kilometers. And the oceanic average it is 5, but it varies between 7 to 8. And as such, silicate rocks, or actually the silicate rocks of granite and oxides, it is slightly dense. Okay, the density, the specific gravity may be slightly lower compared to that of the inner layers. Okay, so the entire mass of the Earth, its contribution is only 5%. Okay, the outermost layer. The next part is the mantle. Okay, the crust is over. Next part is the mantle. The mantle is actually just below the crust as such. Mantle as such may be divided into maybe the upper mantle and the lower mantle. Okay, total thickness of the mantle is approximately 2,900 kilometers as such. Okay, so if in out of which maybe the top corresponding upper mantle may be approximately 400 kilometers. Okay, so the topmost layer is slightly solid. I will call it a semi-solid, and the mantle as such would be almost a fluidic nature. Okay, so most of the deep earthquakes as such may be formed in this corresponding or the upper mantle part. Okay, uh, lower mantle as such will not have any earthquake. The upper mantle also, if there are earthquakes that can happen in the crust as well as the upper mantle. Okay, the specific gravity may be approximately 5, and you see the temperature will be around 2000 degrees Celsius. Okay, so as such, it is due to that heavy corresponding temperature. It is like especially the lower part of the mantle is almost like fluid type. Okay, and but sometimes it has a semi, not purely fluid type, but a plastic nature, almost like it consists of usually what we call heavy metals, okay, of magnesium as well as iron. Okay, the silicate components of magnesium and iron as such, and that corresponding topmost what you call specific gravity is approximately 5 gram per centimeter cube. Okay, and this constitutes almost 65 percentage of the entire Earth's mass. Okay, so a mantle as such, it is not shown here. It is divided into two parts: upper mantle and the lower mantle. Earthquake can occur either in the crust or in the upper mantle. Okay, either the crust here or in the upper mantle. No earthquakes will be occurring in the lower mantle. Okay, and then comes the core. Okay, the core is the innermost part of the Earth's surface. Okay, the core as such, it is also divided into two parts, which consists of an outer core and an inner core. Okay, both the core is also made up of iron itself. So the outer core is usually a liquid type, and hence it is molten iron. And the inner core, it is also made of iron, but since it is solid. Okay, why? Because the corresponding pressure at what you call the inner core is very high, maybe 4 million atms atmospheric pressures, and that's about a very high density, maybe 13.5 gram per centimeter cube, approximately that much dense it is. So due to the action of the high atmospheric pressure, despite having a very high temperature, okay, the temperature is approximately 2500 degrees Celsius. Despite having a very high temperature, at the inner core, due to the very high pressure, it is a solid, okay, compared to that of the outer core. So you can see here the outer core, it's actually liquid nature, and the inner core, it is solid nature. So this is the corresponding approximate layers, the different layers of the Earth. Okay, the inner core, besides iron, there is also nickel. Okay, iron is a primary component, so we also have nickel as such. Okay, 2500 degrees Celsius is approximate what you called a temperature that is there in the inner core as such. Okay, the total radius as such is approximately 3000, maybe 3000 something kilometers, 3470 kilometers of the radius of the core. So this is the basic different layers of the Earth. This is a brief idea of the different corresponding, how the corresponding core are there and what are the corresponding thickness. These thickness, okay, don't consider this to be radius, this thickness. Okay. So as such, I told you earthquakes occur in the crust or in the upper mantle. Okay, in the crust or in the upper mantle. Now, the next thing, as I told you earlier, the Earth was a very molten state. Okay, it was highly toxic. It was not possible for life to exist. Later, when Earth cooled down, okay, as such, you see it the corresponding outer crust solidified to what we see today. The thing is that when it got solidified, the entire part of the earth was almost major part of some parts of the earth was as such one large body mass. Okay, one large body mass. Later, this corresponding body mass got split and moved into different areas. Okay, so this theory which was proposed, since we don't have any direct way of observing these things, a theory was proposed by the German scientist Alfred Wegener in 1915, in which he stated that, or in which it was a hypothesis at that time, in which he stated that as such, the entire large mass means that such the entire continents we see today, okay, it was one single mass or one single area, one single area. It was not divided into different parts. It was one single large area, and as such, this corresponding what you called this corresponding what you call these continents or this what you call these landmass was later drifted to different uh, positions as we see today. Okay, so that is what is given in this statement here. Continents are situated on slabs of rocks, or we call it plates. Okay, as such, it is like the uh, entire solid mass. The crust is such is divided into, or it is broken into a number of pieces. Okay, and then these entire things have drifted to the current areas due to the motion of the molten mantle in the earth surface or under the earth. So as such, when they were joined at one single body mass, it was called a Panagia. Okay, and it was surrounded by a large ocean called the Panthalassa. So the entire body mass today, at that time, was called a Panagia, which later broke and split into the continents which we see today. Okay, so that was the corresponding hypothesis that was proposed by Alfred Wegener. We call it the continental drift theory, even though it is not exactly true, but we had come a large part of his findings were true to some extent. Okay, now he based his observations based on the similarities in the coastlines, okay, of maybe the South America, Africa, India, Antarctica. If you see the coastlines of all of these, it seems that this corresponding entire mass was one. Based on his observations, okay, it looks like they were one mass and then they split apart. Not only that, you see, besides the coastline, even the geology and sometimes even the fossil records show that there is some common links between these two, or between these or four continents. Okay, so the fossil remains that was found, okay, maybe in South Americas and Africa near the coastlines were almost similar. Similarly, in the between the India and Australia as such, there are similar what we call fossils that has been observed. So based upon this corresponding theory, this corresponding studies, he said that the entire thing was one entire mass. Okay, and then they broke out into different pieces. Okay, so that is what his theory was. Okay, to some extent, okay, it may be not entirely true, but he introduced the concept something called plates. Okay, the concept called the slabs of rocks or plates. This is a concept he introduced, which was true. Okay, so now I think I'm not going to much detail regarding this, how it has the different what we call fossil studies, as well as how it is common, which I'll discuss later. Some of the common ones which he had observed are given here. ABC. The fossil of the same plant, that is a Glossopteris, was found in both Australia, India, Antarctica, and South America. Okay, means the same plant fossils were recorded on all these, and you see all of these are here: India, Antarctica, Australia. Okay, this you can see it is mentioned here. The green, okay, the green indicate the areas where these fossils were found, and it was observed to be common in all these areas. Okay, so as such, one thing is that, and a reptile, Mysosaurus, which was found both in Africa as well as South America. So you can see here a corresponding Mysosaurus here. It was observed in both these areas, both the tips of these areas. Okay, similarly, there is another what we called fossil, which was called Cyanognathrus, which is also found both in South America as well as Africa. So depending upon these what we call studies which he had observed, he had come to this corresponding conclusion that they were in fact one corresponding piece or one corresponding entity, and then later split into the different parts. The earlier is called Pangaea. The earlier large continent mass was called the Pangaea, which was surrounded by an ocean called Penthesilea. So this is regarding the continental drift theory. Even though not everything is true, but he got certain aspects true. One is regarding the concept called plates. Okay, as such, you see the crust of the earth is divided into a number of pieces. Okay, into a number of called pieces as such, which are called as plates. Okay, so before that I come to that picture, one thing I would like to remind is that, you see, when I say a crust, okay, the crust and a few upper part of the mantle together is called the lithosphere. Okay, the crust and a few upper part of the mantle is called together is called the lithosphere, and below the lithosphere it is called asthenosphere. This difference in especially this difference comes in geology. This difference as in lithosphere and asthenosphere is based upon the rigidity of the material. I told you the upper part of the mantle is slightly solid, like the crust itself. It is in a almost a plastic state, I call it. We can say plastic state. So both these combined together, we call it the lithosphere, and then the remaining part of the upper mantle as such, I'm not talking about the lower mantle, even the remaining part of the upper mantle, we call it as asthenosphere. So the division based on the rigidity is slightly different compared to the internal layers. Okay, internal layers is something different, and the corresponding lithosphere and asthenosphere division is something different. So you can see that here. Okay, the lithosphere here, a few part of the crust as well as a few part of the upper mantle. Okay, and the asthenosphere, the part of the upper mantle. Okay, below the lithosphere. So to show that figure, I have given you this to show this corresponding distinction. I have shown you this figure here. Okay, so I'm not going to much detailed aspect of this part. Now with you see, there is also a role played by the corresponding fusion of this earth. You see, in the innermost parts of the earth, okay, due to the very high temperature and very high pressure, okay, fusion reaction takes place. That is why the inner parts of the earth does not cool down, except the inner core. Inner core, it is not cooled down. It is due to the very high atmospheric pressure. It is solid. But the rest of the rest of the layers, that is the outer core, the lower mantle, these are all in a liquid state, and this corresponding heat is due to the fusion reaction of the materials at that high temperature and pressure. Okay, the fusion reaction that takes place, not the fission reaction, but the fusion reaction. Okay, so two materials or two atoms collide as such as to form a molecule or a higher atom as such, and a large amount of energy is released. So this is what happens in a fusion reaction. So this is what keeps the inner parts of the earth to high temperatures even today. Okay, so it does not cool down the inner layers. So this is what just hold on. Sorry. So this is regarding continental drift theory, and now we are coming to plate tectonics. Okay, what do you mean by plate? So I told you the corresponding distribution based on rigidity as such. So this corresponding, why I told you this rigidity is that the see in 1951 Alfred Wegener proposed the theory of continental drift. By the 1960s, okay, this corresponding continental drift theory was combined with the theory of seafloor spreading. Seafloor spreading means that in the deep portions of the sea, there are areas where new crust gets developed due to the molten lava comes out. That molten lava as such solidifies and becomes new crust. Okay, so this corresponding continental drift theory as well as the seafloor spreading was combined together to form the theory or to form the corresponding plate tectonic theory. Okay. Hello. So the plate tectonic theory states that the lithosphere, that is the crust as well as the few portions of the upper mantle, is broken into several segments, pieces, which we call it as plates, or we can call it as tectonic plates. Okay. Now these tectonic plates, it is broken. Okay, the entire surface of the earth of the crust is broken into pieces, and these tectonic plates are actually floating. I say it again, the tectonic plates are not constant, but they are floating on the asthenosphere. Okay, that is a liquid part. Okay, so as such, the lithosphere is actually floating over the asthenosphere. That means in another statement is that these things is not constant. We are moving. The entire the lithosphere plates are not constant, but they can move. Okay, they are floating over the weaker and the softer asthenosphere. Okay, you see the corresponding the lithosphere. Okay, is usually considered to be almost 100 kilometers below the continents. That is, if I say 40-kilometer crust plus 60-kilometer of the upper mantle. Under the oceans, it may be 5 to 10 kilometer oceanic crust, and below that may be 40-kilometer lithosphere. Sorry, 40-kilometer upper mantle. Okay, let me show you the figure again. Okay, here say this corresponding crust part is usually in a 5 to 10 kilometer. Okay, this corresponding is usually 40-kilometer average, for example. Okay, the remaining part of the upper mantle is usually 60-kilometer, and here the remaining part, it will be approximately maybe 40-kilometer, 40 to 60. So the entire part, okay, this entire thing is what is called the lithosphere. The total, it will give you approximately 100 kilometer. Approximately 100 kilometers, not exact value, and this will give you approximately 50 kilometers. I don't know if it is visible to you. Okay, this 50 kilometers and this is 100 kilometers. Okay, the lithosphere approximately under the oceans it will be 100 kilometers, and under the corresponding continent it will be almost 50 kilometers. Okay. Now these places, as I told you, are actually moving. They are moving up. It's the moving as such maybe 2 centimeters, 3 centimeters, up to 10 centimeters per year. We are keeping on moving. Okay, these plates are moving. Like you see, for example, you see these ice shelves. Okay, ice shelves is in cold regions, Arctic regions. You see ice shelves, and when it's slightly when the temperature is higher, these ice shelves breaks into pieces and they keep floating. Okay, it is like that. The plate tectonic theory is like that. Okay, the lithospheric plates are floating over the asthenosphere. Okay. Now, why do these corresponding plates move? Okay, why do these corresponding plates move? So these plates move due to the convective currents that are developed in the atmosphere. Okay, the convective currents is like, for example, if you consider heating water. See, when you heat water, what happens? At the bottom place, you're providing the fire.
Hello.
Yes. Who said hello? Okay, I'll continue. So the lower part of the corresponding, if you consider a water that is being heated, okay, I'm providing heat from the bottom. Okay, the lower part of the water gets heated first. Say water is up till this corresponding part. The lower part of the water gets heated. This corresponding water will come up. Okay, and the cooler water will go down. And then this again will get more heated. So the lower water will go up and the cooler water will go down. The same happens in the corresponding astrosphere. Okay, the outer core part, okay, or the topmost, these areas are extremely high in temperature. 2500 degrees Celsius is the temperature in the core. Okay, so and at that, as you come to the top, the temperature is lesser. Okay, so what happens due to the difference in the temperature from top to bottom? These currents are developed. These currents are developed, which we call as convective currents. Okay, which we call as convective currents. Okay, convective currents. Okay, so this corresponding convective currents is the current. These are very heavy, what we call large force. Okay, large forces which corresponding moves the plates. Okay, and this corresponding temperature, as told you, it may be caused due to either the fusion reaction in the core, or it may be even caused due to radioactive decay that occurs in the core itself. So as such, these currents will keep on moving. So what happens, for example, you can see here, as the currents are in this direction, you see this corresponding plate here is moving in this direction. Similarly, this corresponding plate is moving in this direction. So as such, when it moves, okay, some empty portion will be developed here. When this plate will move this direction, this plate will move this direction, then the corresponding some gap is formed in which new crust gets developed. New crust gets developed due to the cooling down of that lava. And certain areas, okay, what happens is that this corresponding crust goes one below the other. Okay, you have one plate here, we call it plate. Now I'll avoid the term lithosphere, I'll call plates. So you have one plate here, you have another plate here. Due to two plates, as such, this area of this is an area where there are two of a plate boundary. So one plate is going beneath the other plate. Okay, so as such, when it goes beneath the other plate, this gets molten, and finally it becomes part of the astrosphere. And so as such, this corresponding plate is being continuously formed as well as destroyed. Okay, this corresponding plate is continuously being formed as well as destroyed. So it is this actual motion that causes earthquakes, volcanoes, as well as mountain ranges, especially in plate boundaries. Okay, so you will have earthquakes, volcanoes, as well as mountainous ranges, especially occurs in the plate boundaries. Now, as such, the Earth is divided into 7 major tectonic plates. Okay, 7 major tectonic plates and a large number of minor plates also, which shall discuss later. So you can see the African plate, the Eurasian plate, the Indo-Australian plate, the South American plate, the North American plate, the Pacific plate, 1, 2, 3, 4, 5, 6, and the North American, there's one more plate, the Antarctic plate. These are the 7 major plates. Besides this, there are large number of minor plates also, like the NASA plate, and you can see the Arabian plate. There are a number of the Caribbean plate. There are a number of minor plates also. So you have got 7 major plates and all the corresponding minor plates. And you see arrows are shown here. These arrows indicate the portion where the corresponding plates are moving. For example, along the in the boundary of the African plate and the South American plate, this is moving towards left and this is moving towards right. Okay, they are moving apart. This is called a divergent boundary. We call it divergent boundary. We'll discuss that later. Okay, and in which they are moving together. For example, here in the Indo-Australian plate is moving upward and this is moving downward. So this is actually a convergent boundary. The Himalayas have been formed here due to the convergent boundary. The Himalayas are formed here due to the convergent boundary here. We'll discuss that later how it is. And then you have got transform boundaries. Transform boundary is that one plate is moving in one direction. Okay, the other plate here, for example, here. Okay, this plate is moving in one direction and this plate is moving in the other direction. So it's like a shear type, like shear. So these are the 7. These are some of the major plates. As such, you have 7 major plates and a large number of minor plates. Okay, only a few plates are shown here. Okay, NASA plate and Scotia plate, Caribbean plate, Arabian plate. These are some of the small subplates. So these corresponding plates as such is moving. As I told you, they may be moving maybe 2 centimeters up to 10 centimeters per year. So as these corresponding plates are moving, the continents are as such are also in one term. Remember one thing, when I say a plate, it includes both the continent as well as the sea. Okay, a plate as such is the actual lithosphere. Okay, that includes both continents as well as seas. It is not that it's only a continent. Don't think consider. For example, you can see the country of Africa here. The country of Africa is this one. Okay, this is African, sorry, not country, sorry, continent. This is African continent, and then there are parts of the sea that is also part of this plate. Okay, for example, the Indo-Australian plate. You have India here. You have the corresponding Arabian Sea here. Bay of Bengal here. You have the corresponding rest of the sea here, and then you have the Australia here. So it includes both the country as well as the seas. Okay, it is not that it's only a what we call a country. It is, remember one thing. It is the upper part, the crust plus the upper part of the mantle, the upper part of the upper mantle. Together we call it as lithosphere or we call it as plates. Now, so as I told you, it is these corresponding plates keep on moving yearly, depending 2 centimeters to 10 centimeters is the average speed. So if you look, as I told you, most of the earthquakes, volcanoes, and mountain ranges are near the plate boundaries. This plate, how did we get to the plate boundaries? We got the plate boundaries only by observing the earthquakes and volcanoes. So you see, there is a volcano or an earthquake along these corresponding spots here indicate both volcanoes as well as what we call earthquakes. Okay, and here you see this corresponding here, and then you have something like this. Okay, the plate boundaries has been we had come to know regarding the plate boundaries by looking at these earthquakes and volcanoes. So you see here on this left hand side, this actually is the corresponding Pacific plate here, the same boundary. Okay, and you can see here one small thing, one small plate here. This actually is the NASA plate here, and then you have the North American plate here. Here you have the Indo-Australian plate here. Okay, so here you have the African plate here. Okay, so we have come to know the corresponding plate boundaries based on the volcanic activity burst and the earthquakes. The majority of the earthquakes will occur, maybe 80% of the earthquakes occurs only at plate boundaries. More than 80% of the earthquakes occurs at the plate boundaries. Okay, so that is how we came to understand about the plate tectonic theory. Fine. Okay, so the earthquake that occurs at a plate boundary is called interplate earthquake. Okay, interplate earthquake. Most of the earthquakes, that is 80% of the earthquakes, occur at the plate boundaries, and the rest also occur within the plates. Okay, that doesn't mean that all earthquakes occur at plate boundary. 80% occurs in the plate boundary. The rest also occurs within the plate due to other conditions. Okay, so based upon how these corresponding plates interact with each other, the plate boundaries has been classified into three. As I told you earlier, the convergent boundary, the divergent boundary, and the transform boundary. Convergent, divergent, and the transform. So first we shall come across the convergent boundary. So when, as I told you, it's simple. When two plates move towards each other, it is called a convergent boundary. So when the two corresponding plates meet each other, two things can happen. One, either one plate could slip below the other. Okay, one plate will go below the other. Or second thing is that both will collide with each other to form something called a mountainous region. Okay, these two happens. Okay, now this collision can happen uh, between a continent and oceanic crust. Between oceanic, some plates occur only in oceans. Okay, some plates is partly ocean and partly what you call continent. Some are only continents. For example, if you see this corresponding figure here, you see the Pacific plate here. The Pacific plate here, it is fully an oceanic plate here. Okay, but if you see the African plate here, it consists of both the continent as well as the ocean. Okay, certain plates are fully oceans, certain plates are fully continents, certain plates are a mixture of both oceans as well as continents. Okay, now convergent boundaries are of two types. One is subduction and the other is collision. As I told you, one is going, subduction is one plate is slipping under the other, and the second one is collision. That means one plate, both the plates are colliding with each other to form certain mountainous regions. Okay, so as such, subduction boundaries, the first one. These boundaries are created when either the oceanic lithospheric subducts beneath the oceanic, means one plate at the oceanic point, okay, is going below the other plate near the ocean part. Okay, this is called a one type. The other type is that between the ocean as well as a continental plate. Okay, so as such, what happens is that when this corresponding happens here, you will find a trench here. A trench will be developed here, and due to this corresponding plate going below this, a large number of volcanic activities occur. Okay, a large number of volcanic activities occur, and also you may find something called land island arcs. Islands get developed in the ocean where there is a convergent boundary in the ocean. Now, when a convergent boundary occurs at the junction of the ocean and a continent, here also you will see volcanic activity. Here also you will see a trench here. Okay, but instead of islands here, you see here island arcs, you will have a slightly mountainous region here. That is the only difference here. So as such, either oceanic lithospheric subducts beneath the oceanic lithosphere, means one ocean lithosphere subducts below another ocean lithosphere, or one oceanic lithosphere subducts beneath the continental lithosphere, means this corresponding oceanic lithosphere is going below the continental lithosphere. This happens. Okay, so as such, what happens is that very high, as the corresponding plate gets subducted into the mantle or into the below into the mantle, what happens is that very high temperatures that develop, very high temperatures within the mantle will what you call crush or will make the corresponding subducted part of the crust as molten, and then it becomes part of the uh, asthenosphere as such. Okay, so one thing that usually happens is that a chain of volcanoes, I told you a chain of volcanoes can be developed, and then if it is an oceanic area, you can get something called island arcs here. The best example is the Indo-Australian plate is subducting below the Andaman and Sunda plates. Andaman and Sunda plates is actually a small subplate, occurs near the Andaman area. As such, it is a place of subduction boundary. The second is collision boundaries. Collision boundaries occurs when two continental plates or when the plates come close to each other near the continents. Okay, so as such, you see when two continental plates come to each other, one will get subducted below the other. It's not like getting subducted, it gets subducted, but what happens is that a mountainous range will be developed. A mountainous range will be developed here. Okay, and in this corresponding area, volcanoes rarely exist. Okay, volcanoes as such do not exist under these areas. Volcanoes exist only in these two cases, in the subduction boundaries when in the ocean or when ocean and the corresponding continent plates crush each other or come close to each other. So these are two different types of convergent boundaries. One is subduction boundary, the other it is collision boundary. The best example of the collision boundary is the Himalayas. The Himalayas as such has been formed due to the effect of the combining or the conversion of the Indo-Australian plate and the Eurasian plate. Okay, I showed you in that plate boundary figure here. You can see here. Okay, you can see here, this is the Indo-Australian plate here and this is the Eurasian plate here, and they are combining. This is convergent boundary. These two are continental plates here at this end. Okay, so they are converging here. So when they converge here, one gets subducted. The Indo-Australian plate is actually going under the Eurasian plate, but as the Eurasian plate is over it, it goes more up, forming the Himalayas. Okay. Now the next type is divergent. Divergent, it is actually the two oceanic plates or two plates are moving apart from each other. Divergent plate boundaries usually occur in oceans. Okay, so as corresponding two plates are moving apart from each other, new corresponding what you called lava comes to the surface from the asthenosphere and they cool down to form new crust. Okay, this is something called a sea floor spreading. Okay, it was actually proposed by Harry Hess in the 1916 itself. Then a hot magma, that means the corresponding hot lava, rises from the astrosphere into the existing oceanic crust through fractures. The fractures that has been formed by the two plates moving apart from each other. So the crust spreads, making room for the new magma to flow up. And then later, the magma cools down, forming new sea floor. Okay, so this is how it's done. New sea floor is created at the corresponding area, and you see, since as I told you, since new corresponding sea floor is being developed, the sea floor as such usually it is made of basalt. Okay, the volcanic material is actually basalt. That is why, as I told you in the first slides, that oceanic crust is usually made up of basaltic materials rather than continental is usually made of granite, while the oceanic crust is made up of basalt. So when this corresponding cools down, when the magma cools down, we get something called a mid-ocean ridge. I showed you in the first figure here. A ridge is being developed. Okay, the area where the new crust gets developed. Okay, so here you can see it in the figure here. Okay, these two plates are moving apart from each other. So as such, new molten magma comes out and they form new crust. So you got something. You'll see a certain area like this, which consists of we call it as a mid-oceanic ridge. Okay, you see here in the figure here, this corresponding red thing is actually the Oceanic Ridge here. This is actually a not photograph. It's actually from satellite photo that it is an American satellite that's taken this photo. Photo in the sense it is a photo that studies the surface of the Earth. So they had observed this corresponding mid-oceanic ridge that has been developed. I think it is between Pacific Plate and Indo. What you call it? Pacific Plate and the American South American Plate. The next thing is transform boundary. Transform boundary is like two plates are moving in two different directions. They are not coming together, they are not moving apart, but they are having like a shear force, you see, like that they are forming like this. Okay, they are moving in opposite directions. Okay, and this is also a very high region, earthquake prone region, where there is transform boundaries. Okay, due to the movement. So as such, all these things has been given in one single figure here. Okay, all the corresponding the ridge here ridge where two oceanic plates are moving apart from each other. So don't it's not a ridge. Ridge is where I think ridge is not shown here. Okay, here the two corresponding oceanic plates are coming to each other. So one gets subducted in the other, forming an island arcs here. Here is an area of subduction. Here there is another area. Here there is another one. All different types of boundaries. You see, this is given as convergent boundary. This is a transform boundary, going both different directions. This is a divergent boundary within the ocean. This is also a convergent boundary that is between the ocean as well as the continent. Everything is being given in one figure. It's actually a figure from the Encyclopedia Britannica. So what we had discussed till now is what occurs near the plate boundaries. Okay, what occurs near the plate boundaries. Now that is not only the area where earthquakes are formed. Earthquakes are also formed in areas within the plates. We call it one is intraplate earthquakes, the other is interplate earthquakes. So as such, why do earthquakes occur within the corresponding plate? Within a plate, why earthquake occurs? So when we come to study the corresponding when we come to investigate this corresponding concept, we had studied that there is something called faults that are developed within the plate itself. There's something called faults that are developed within the plate itself. The fault is actually a discontinuity in the rock mass. Now remember one thing, we are not talking of plates. Okay, now we are talking of maybe the small part of the upper crust. Okay, not the full crust. Okay, the small part of the upper crust. Okay, where there is a chance of discontinuity in the rock mass due to some things that has happened in the past. Maybe it may be due to a meteorite strike, or it may be due to some other activity on the surface of the earth. Okay, there may be faults that occur over the period of time. Okay, and there are different causes of faults. We are not going to that aspect, but faults are areas where there is a discontinuity in the rock mass. Okay, not the entire crust. Okay, don't take it. We have finished plates. Now we are coming to within the plate. Okay, so as such, depending upon the nature of fault, faults are classified into either normal faults or reverse faults. Hold on. No, there are more. Don't consider this, okay, for the time being. Faults. There are more types. Now, before I go into much detail regarding this, I think you must have discussed this, learned this in geology. I'm not sure. So, as such, faults, there are certain technical terms that you have to study in faults. One is the corresponding strike. Now, strike is actually the direction of the horizontal line on the surface of the fault. You see in this figure here, you have an area of strike here, okay, out of which one wall is called the foot wall and the other wall is called the hanging wall. Okay, the one which is at the top, it is called the foot wall. The other which is at the bottom is called the hanging wall. We call the overlying surface. Depending upon the overlying surface, one that is above we call it foot wall. The below one we call it the hanging wall. Now the vertical shift, okay, the vertical distance between the two walls or the two corresponding thing is called throw, and the horizontal distance, this distance is called the heave. The vertical displacement that has occurred is called the throw, and the horizontal displacement that has occurred is called the heave. You see, even though it is occurring in an inclined way, the horizontal and the vertical distance is what we are talking about. Okay, and then we have something called the strike angle. In case then we have got dip vector. Dip slip is actually the corresponding inclined position. Okay, both considering the heave as well as throw, the resultant of that, this is called the dip. Okay, we shall discuss all this thing later. We are not going to much detail regarding this one. This one I had just shown you the different types of faults that occur. One is the normal fault, the reverse fault, strike slip fault, and oblique slip faults. Okay, so in the normal fault which is shown here, okay, you have the hanging wall, and you can see in this figure here, this is a foot wall, this is the hanging wall. So let me show you another figure. We'll discuss to understand better. We'll discuss this figure. Now, first normal faults here. Now, if two blocks of the crust, okay, is moving away, means one is moving the other direction, the other is moving the other direction. Okay, so what happens is that maybe due to some tension forces, we are not going deeper that part. So the hanging wall will be displaced downwards compared to the foot wall. Okay, this is hanging wall. This is foot wall. Okay, your hanging wall goes, if this corresponding plate goes this side, not plate, this corresponding rock mass goes this side and this corresponding rock mass goes this side, what happens is that this rock mass will go below and this rock mass will go up. Okay, depending upon how the angle is. This angle is called the fault plane. Okay, this is called the fault plane. Since you have a discontinuity in the rock mass here, due to some effect that has been caused, some natural effects, some volcanoes, some earthquakes, okay, as such has caused this fault here. So when these two parts, remember one thing, I'm not talking of the plate. Okay, there is not a plate. Okay, this is just a rock mass. So one rock mass goes towards left, the other rock mass goes towards right. So what happens when the angle is like this? This will go down, this will be up. Okay, the direction is shown here. This is called a normal fault. The hanging wall is going down and the foot wall is going up. This happens when both the plates are moving away from each other. Okay, this is called a normal fault. So normal faults will result in entire mountain ranges to be developed. Okay, you can see the mountain ranges that are shown here. Okay, when this corresponding moves up, you can these mountainous regions are formed here. Okay, it is also called as fault block mountains. fault block mountains. The other is reverse fault. In reverse fault, what happens is that both these block masses move towards each other. So as such, mountainous regions are formed in both these areas. Okay, but here what happens is that the corresponding hanging wall goes up compared to the foot wall. Okay, that is why it is called reverse. Okay, the hanging wall goes up compared to the foot wall. It is based upon this angle. Okay, remember this angle has already been caused, okay, due to some factors. Okay, the fault plane is this one. So based upon this, if it was like this, it will be in different direction. The motion will be in different direction. So since this has already been formed here, this is called a reverse fault. Okay, so the hanging wall has been displaced upward relative to the foot wall. Okay, formed during continent to continent collision. Usually there is also accompanying folding of rocks. Folding of rocks occurs in both directions, resulting in mountainous regions on either side. The next is strike fault. Strike fault is due to the two blocks. Remember one thing, not plates. Okay, the two blocks of mass moving in like in shear. Okay, so this corresponding thing is also called a transcurrent fault or a wrench fault or a lateral fault. Okay, so depending upon the direction of the offset, okay, it can be either a right lateral offset or a left lateral offset. Okay, we'll discuss. We're not going to the deeper part regarding that aspect. And the best example of this is San Andreas fault in America. Okay, the strike faults. Strike faults comparatively are lower. Okay, means lower in the sense the amount of number of faults, strike faults are comparatively less compared to normal reverse faults. So that is all with regards to the Earth's what you called the Earth structure and how all these faults will also cause earthquakes. So earthquakes can occur either at the plate boundaries or earthquakes can occur at faults. Okay, earthquakes can occur either at plate boundaries. We call it interplate intraplate earthquakes, or it can occur within the plates itself due to the different faults that occur. Okay, that is called interplate earthquake. Interplate earthquakes. Now, fault is one reason. Okay, volcanoes also can cause earthquakes. These are also other aspects. We're not going into much detail regarding that. So first, since we have already studied the basics of the Earth structure, we shall go into some of the basic parts of an earthquake. Now, what is an earthquake? Earthquake as such is the vibration of the surface of the Earth. Okay, not the surface. It's the vibration of the Earth's surface that is caused by the waves that is coming from a particular disturbance. Okay, a disturbance in the Earth. Okay, now as I told you earlier, most of the earthquakes are due to the tectonic activities at the plate boundaries. Okay, so it occurs due to the corresponding movement of the plates here. But besides this, earthquakes can also be caused within and most of the earthquakes are caused either due to the tectonic plates or maybe due to the faults. 80% due to tectonic, maybe 15% somewhat with respect to faults, and the rest may be caused due to volcanic activities. It may be due to other natural or man-made causes like explosions, landslides, even heavy traffic movements, as well as engineering constructions can also cause earthquakes. This may be usually maybe 2%, etc. Okay, so majority of them are caused by tectonic origin. Then a part of it, 15 to maybe 18%, it varies, maybe geological faults, and then the rest may be caused due to other actions such as volcanic, as well as the remaining parts, maybe 2% as such, will result in this. Okay, so these is what the corresponding this. What are the characteristics of an earthquake that has been occurring due to tectonic activity? Okay, if the corresponding tectonic activity is there, what are the typical what are the characters that define a plate of an earthquake of tectonic origin? Okay, it depends upon the stress drop that is there occurring during the slip, the total fault displacement, the slice of slipped area, roughness, fault shape, proximity, soil condition. Both are the tectonic as well as faults. Okay. And there's no need of studying this one. It's just this one. Now, as such, I told you how an earthquake is formed at tectonic boundaries or at plate boundaries. Okay, you see, tectonic plates are actually elastic materials. Okay, it doesn't mean that they're elastic materials in the sense that not exactly.
Excuse me, sir.
Huh.
Sir, what does this tectonic mean, sir? Tectonic word means?
Tectonic as such is it's related to what we call tectonic activity. That means related to a disturbance in the Earth's surface.
Sir. And sir, why upper mantle is considered in lithosphere?
I told it is based upon the rigidity. The upper part of the upper mantle is almost solid. The upper part of the upper mantle is what we call the solid part. It is based on rigidity that it is divided into what we call lithosphere and asthenosphere. It is not based upon the what we call the crust. Okay. There's a difference between those two.
And sir, what is features of asthenosphere, sir?
Features of asthenosphere matlab?
मतलब सर
Liquid
क्या करता है
format.
क्या गैस है सर
Molten
क्रस्ट
liquid.
का लिक्विड है ओनली
The
Okay, sir, thank
lithosphere is solid as such. The asthenosphere is molten liquid.
Okay, sir, got
Okay, so what I was saying regarding elastic, I was talking regarding tectonic plates. You see, tectonic plates are elastic, but they're not very elastic like you have a rubber band or something like that. They have slightly elastic nature like any other materials as such which is being formed like something. They are elastic but brittle. Okay, so what happens is that when two tectonic plates move, okay, either at a convergent boundary or at a transform boundary, when they move here, they first, as such, they cannot move very easily because they are striking against each other. Okay, so I'll show you a figure to help you better understand it. Okay, this is an example of a fault zone. Okay, as two tectonic plates or things move here, as these corresponding things move here, you see in the first case here, the plate tends to bend. Okay, the plate as such tends to bend, or sometimes what happens is that the strain energy gets collected within the materials of the solid. Okay, within the materials of the solid, the strain energy gets absorbed in the materials, and finally, when the corresponding stress value reaches an extreme limit, okay, that it can be carried by the rock. Okay, when it reaches the ultimate point, then at that time sudden movement takes place. It breaks free. Okay, a sudden movement takes place. This corresponding sudden movement results in the releasing of the entire strain energy that is carried by the rocks. Okay, the entire strain energy that was carried by the rocks at that interface, okay, it gets released. Okay, and that corresponding thing is what produces the earthquake. I'll show you just if I on my video. See, I have two plates here like this, for example. Okay, when I try to move two plates like this, first what happens is that I'm applying pressure. This hand is going upwards, this hand is going downwards. I try to apply pressure. This corresponding thing at the surface, strain energy gets developed at this two interfaces. Okay, it is due to that extreme, since they are closely they are very close, and as such they are interacting each other. It may not be very easy to split them apart. So first what happens is strain energy gets what you call developed at both of these, and finally at one point it moves. So when it moves, the entire strain energy that has been collected by at the interface gets released at one instant of time, which will result in an earthquake, or which will result in that seismic waves that it will travel throughout. So this is what happens. Okay, so I'll off this one. The reason why I'm offing this one is that you will not concentrate on the slide, you will concentrate on my movements. Okay, so I think I had gone somewhere else. Is my screen visible to you right now?
Yes, sir, it is visible.
Okay. So this corresponding theory is called elastic rebound theory. Okay, elastic rebound theory. The sudden slip at the point of fault, or it may be a tectonic boundary. This is the correct thing. This is the cause of an earthquake, or this is the cause of the energy being released. Okay, so this elastic strain energy that is released will travel in all directions in the form of waves, which we call it as seismic waves. Okay, throughout the entire earth. It may go deep down, or it may be, depending upon the size of the earthquake, it may be very large waves or it may be small waves. So these may travel throughout the body of the earth, as well as it will travel also on the surface. Okay, so what happens is that entire energy gets relieved at one instant of time. So that energy release is what the wave results in these seismic waves. Okay, so you can see here a corresponding graph here. Okay, you see the first, if you see at the bottom here, the elastic stress that is developed in the rocks. Okay, with time. So as such, this time means this. When I say it gets released, it takes large years. Okay, it's not at 1 minute or one thing. It takes large years to get the entire strain energy collected. And at one instant of time, when a slip occurs, it releases at one point of time. So you see here, you can see the elastic stress in the rock material get increased to an extent that when it reaches the ultimate strength of that corresponding rock, okay, entire thing is released. Okay, so at one instant of time, the entire thing will go down. Okay, again it will go up. Again, as the movement continues, the movement will not stop. You see, these corresponding convective currents are continuous, so the movement will be keep on moving. So as such, again it will get built up. Okay, and again it will be released. Again it will be built up. Again it will be released. Okay, so as such, in these plate boundaries or at the faults, energy gets built up and then gets released. So that release is what will actually cause the earthquakes, and this is actually that take years. Okay, it will take years in order to get the energy accumulated at one point of over time and then released at one instant of time. Okay, the accumulation takes place over a large period, but the release occurs within seconds or minutes. Okay, so this is what happens. The slip, you can hear the slip. The slip keeps on increasing. This means that the first slip, say it may be 2 centimeter slip. Okay, at point here, when it gets suddenly released, means the two corresponding plates or faults move away, it becomes 3 centimeter. Then the slip is 4 centimeter, cumulative slip finally maybe 5 centimeter, 6 centimeter, 7 centimeter, etc. It keeps on moving. Okay, it keeps on moving. Okay. Okay. Just give me a minute. Okay. अच्छा तो सर वो ले लो वो मुक जाएगा चार्ज हो गया. So this is how the corresponding elastic gets accumulated and released at one instant of time. Now, what are the different terminologies which we use in an earthquake? I think you must have already studied this. I'm not going into much detail. One is regarding the focus or hypocenter. Okay, the portion, the point is actually wrong. The portion where the fault or the slip has caused, okay, resulting in the earthquake, that is called the focus or the hypocenter. Okay, the area. Okay, we cannot consider it to be a point, even though most textbooks give it as a point. It's not actually a point. It is actually an area. It's actually or maybe for example a portion. Okay, an area or a portion. We don't consider it a point. So the area on the fault where the slip has initiated is called a focus or the hypocenter. Okay, you can see here in modern seismology, the focus signifies a zone rather than a point of origin. Okay, most textbooks use the word point, but it's not right. Point is not right. So it may be maybe a few hundred meters, or maybe it may be even kilometers below the surface. Okay, so that's why we can call it as a point. So depending upon where this rupture has occurred, okay, it may be highly irregular, it may be or a large area, it may be a small area. As such, focus or hypocenter is the portion where the slip has initiated. This next sentence, I just show you a figure here. So here, for example, this is a focus. Okay, it's not a point here, it may be an entire area here. Okay, it may not be like a point here as such, it may be an entire area where the focus or was the earthquake has been initiated. Okay, now epicenter is the distance directly above the focus on the surface of the earth. Okay, the geological place on the surface of the earth which lies exactly above the center of the earthquake, means exactly above the focus, that is called epicenter. Okay, in most cases the waves reach the epicenter first, and hence the epicenter is the center where the maximum damage usually occurs generally. Okay, epicenter is a location where the maximum damage occur because it has the greatest amount of seismic waves will come to the epicenter. Okay, now focal depth is actually the depth from the epicenter to the focus. Okay, we call it focal depth. Okay, so it also determines the damaging potential. Means if the focal depth is very large, then it becomes less what you call intense. If it is very close to the surface of the earth, it becomes more intense. So the most damaging earthquakes will have focal depth less than 70 kilometer. Now there is classification of earthquakes depending upon focal depth. We'll discuss that later. It is between 70. So if it's less than 70 to 300, or greater than 300, we'll discuss that later for time being. So focal depth. Okay. So here the entire thing is shown here once again. The focal depth, the epicenter, as well as the focus. Now the distance between the epicenter and a point of interest. A point of interest may be a site, which may be either be a building, or it may be some the seismic instrument where we have kept our instrument for measuring the earthquake. Any site, this corresponding distance is called the epicentral distance. Okay, so and this corresponding distance between the focus and our site or the point of interest, not site, we call it point of interest, is called hypocentral distance. Okay, so as the corresponding epicenter distances increases, the greater and greater the corresponding our location is from the focus or from the epicenter, okay, the less is the damage, because by that time the seismic waves will almost die down. Okay, the more the distance. Okay, next we talk about seismic waves. Okay, what are the waves that developed? Now, seismic waves are actually elastic waves. Like you have when I drop a pebble in a surface of water, ripples get developed, okay, or waves get developed. Okay, similarly, if you have sound waves, okay, similar like that, earthquake, the seismic waves are actually elastic waves that gets generated at the point of the earthquake and then travel in all the directions. Okay, so when they travel in all the directions, you see, as such, the Earth's surface consists of different layers. Okay, depending upon even the crust as such has got a number of layers. Layers depending upon there is a difference in the density. Okay, as I told you, density is not, when I said density of the Earth's crust is 1.5 gram per centimeter cube, it doesn't mean that it is 1.5 everywhere. No, the densities keep on varying. Okay, at the top it will be less. If you go to the bottom, it will become more different. So there are different layers as such. So entire the Earth's surface, okay, and the interior of the Earth has a number of layers. Okay, so as such, when these waves get developed, they undergo these waves like elastic waves, like light waves as such. They have multiple reflections and refractions that occur. Okay, dispersion takes place, refractions occur as they and attenuate. Attenuate means they die down. So as they either may get reflected, refracted, they die down depending upon how they travel. Okay, so the entire corresponding study of the seismic waves. I told you earlier, the seismic waves, the generation, the propagation, as such, that study is called seismology, and it's actually a branch of the geophysics. Geophysics is actually the study of the Earth. Okay, the geophysics includes geology, okay, seismology. These aspects all comes under geology, all comes under the geophysics. So these aspects, the study of seismic waves as such, is called seismology. Now there are two types of waves that are developed. Okay, when earthquake happens, okay, one is body wave and the other is surface wave. One is called body wave and the other is called surface wave. Body waves are actually the waves that travel throughout the interior of the earth, interior of the throughout the body, not at the surface, to the interior portion of the earth, and they travel in all directions. Okay, they consist of two waves, primary waves and secondary waves, which I'll discuss this later. So when the corresponding P waves or the body waves reach the surface of the earth, most of the corresponding body waves get deflected back within the earth itself. Okay, the body waves reach the surface of the earth, they get reflected back into the interior of the body itself. Okay, the body waves. The second type of waves is called the surface waves. You see, as the body waves reach the surface of the earth, a part of these body waves will force the other waves to get developed at the surface. Okay, these body waves, as a result of these body waves, when they reach the top of the earth and they get reflected back, this corresponds at the time of reflection, a part of that energy gets transferred to the surface, and this will result in waves being developed at the surface. Okay, these are called surface waves. Okay, they are comparatively slower. Body waves are more faster. Surface waves are much more, means they travel much more slowly, and it is, we usually as such, the surface waves as such is most destructive. Okay, because it has got a very complex path. We'll discuss it later how it is complex. We have got a very complex path, means how they move is very complex, and they may be as I told you, they are divided into either Rayleigh waves or love waves. Like primary waves, body waves are divided into primary waves and secondary waves. Similarly, surface waves are divided into Rayleigh waves and love waves. Okay. Now I'm talking of seismic waves. Seismic waves, of which I'm talking of body waves, of which one of the waves is primary wave. Now, primary waves are also called as P waves, push-pull waves, or longitudinal waves, or compressional waves. All these terms indicate the same thing. Okay, whether we call P wave or push-pull wave or longitudinal wave or compressional wave, all these corresponding waves indicate the same thing. This is like the sound waves. You see, the particles of the corresponding material through which this wave pass actually move what you call move in the direction of the wave transfer, like sound waves. So you have alternate regions of compression and expansion. Okay, like in a spring here, you see it is shown here. An example is shown here. Okay, sound waves also travel in the same format. Okay, so as such, there are alternate areas where there is compressional strains and then extensional strains. Okay, there are alternate areas. For example, this is an extensional strain and this is a compressional strain. Okay, so as such, when I release this, as such, the particles here will move in this direction, in the direction of the wave propagation. So you can see in this figure here. Okay, this is the example of an undisturbed region. Okay, but when A gets formed, you have compression, which is shown here, close lines. Here also is close line, and expansion, where is more apart. So due to that, like sound waves, how it travels the same way the primary waves, it's the type of body waves travel. Okay, and they are the fastest. They are the fastest. They travel approximately 4 to 7 kilometers per second, and they're capable of traveling in all mediums: solid, liquid, gas, etc. Okay, solid, liquid, gas, as such, they can travel through all mediums as such. The second wave is secondary waves. The secondary waves is like we also called as S waves or shear waves or transverse waves. It is like that ripples that is formed on the surface of the water. Okay, so here the thing is that the material particles as such oscillate perpendicular to the direction of the wave. Okay, the material particles as such oscillate perpendicular to the direction of the wave. Here on the other hand, they oscillate in the direction of the propagation of wave, but here they oscillate perpendicular to the direction of the propagation of the wave. Okay, they are comparatively slower compared to the P waves. Okay, and they as such, you see, this corresponding S wave can either be in this direction or in this direction. Okay, the wave propagation is like this. Okay, it may be moving in this plane, in the vertical plane, or may be moving in the horizontal plane. Okay, so as such, it can be split into horizontal as well as vertical components. Okay, sometimes maybe at an angle also. So as such, it can be distributed, or it can be divided into the horizontal component as well as the vertical component. And this corresponding waves as such can travel only through solids. Okay, as such, within the material, what you call, let me just reduce this size here. Sorry. Okay. Sorry, they can travel not only they can travel both. They can travel in both solids as well as liquids. Okay, body waves as such can travel both in solids as well as liquids. Okay, I think it is shown in the first figure. Okay, fine. The next is surface waves, secondary waves. The next is surface waves. Surface waves are of two types, as I told you, love waves and Rayleigh waves. Love waves are similar to the S waves, but they have only the horizontal component. Now, as I told you, surface waves occur only at the surface. Okay, these waves are caused only at the surface of the earth, and they are the surface waves are the most dangerous because they cause the more damages to life and property. whether there is destruction of buildings, there is the loss of life, whatever it is caused due to the surface waves. The interior, the body waves as such, you see, they travel in all directions. Okay, so we'll show that figure later. So as such, the surface wave are two types, love waves and Rayleigh waves, in which the love waves are similar to that of the S waves, which is a body wave, but they have only the horizontal component, no vertical component. So they are moving perpendicular to the direction of space, but only in the horizontal direction. Okay, you can see here, they move in this direction. The wave propagation is in this direction, and they move like this. Okay, here they can move only through solids. The next wave is Rayleigh wave. Rayleigh wave is also that occur at the surface of the earth, not within the body. Remember one thing, don't take this to be at the surface. Okay, this occurs within the body, not only the surface, but within the body. Okay, now Rayleigh wave as such is similar to that of the primary P waves. Okay, which is a body wave. Okay, but it has an elliptical path. The material as such has an elliptical travel path. Okay, I can see here there's an elliptical shaped travel path that is shown here in this figure here. Okay, and hence they are capable of traveling through solids as well as liquids, but not gases. So 4 types of waves, 2 body waves and 2 surface waves. I told you earlier, okay, the seismic waves can get reflected, can get refracted. Okay, it's called seismic reflection and seismic refraction. Okay, depending upon the properties of the different layers of rock. Okay, different layers of the rock, they may get reflected as well as refracted. Okay, we had actually the corresponding different layers of the earth, the crust and the mantle, the inner mantle, upper mantle, etc. All these we have come to know about this only from the study of the seismic waves, not by drilling into the earth's core. We have never drilled into the earth's core. By studying the corresponding properties of seismic waves, we have studied regarding the earth's interior layers. Okay, here is an example of how the corresponding waves get transmitted throughout. Okay, so here at the one point, epicenter no, it is actually a focus. It is slightly below the corresponding crust. Okay, since it's a very large scale, you cannot see the crust thickness properly here. So as such, the P waves and the S waves, which are actually the body waves, gets transmitted throughout the interior of the earth. Depending upon how large the earthquake is, they may travel to great distances. Okay, they may travel to great distances. Okay, so as such, you can see the waves traveling here, the P and the S waves. Okay, so the P waves as such travel through the P and the S. The P waves travel through only the solids and liquids. So the P waves travel only through the liquid, not the solids. So as such, you can see there may be areas where there are no P waves. There may be areas where there are no P waves. So depending upon these studies, we have come to know these layers, how this corresponding crust is there, since it is solid, liquid. All these study has been studied based upon this corresponding study. Okay, so here there is no P waves, here there is no P waves, here there is no S waves. So depending upon these studies, we have come to know the structure of the earth, the interior of the earth. Okay, so P and S seismic waves have helped seismologists in understanding the nature of the interior and core of the earth. Okay, and remember one thing: if a corresponding earthquake occurs at a point, we have a large number of seismic locations to measure the earthquake. Okay, we'll come to that measurement later. So depending upon that measurement, we may be able to identify from which point the earthquake focus is, or which is the epicenter distance. Sorry, not epicenter distance, which is the point of the epicenter, or which is the point of the focus. So depending upon that, they had come to study regarding the Earth's interior. Now, how the corresponding how the corresponding seismologists study the what you called the epicenter location based upon the speed of the P and S waves. Okay, it is based upon the speed of P and S waves. Why? Because the P waves travel faster. The P and S waves travel faster compared to the S waves. Okay, so by measuring the difference between the P waves and the means the body waves and the surface waves, one can identify the distance of the focus or the epicenter from our site. So for example, these are what you called a graph that is shown here. Okay, so you can see the first to arrive is the P waves, since they are the fastest. The second to arrive is the S waves. Both travel through the body of the earth. Both travel to the body of the earth. And then comes the surface waves, which cause the maximum damage, which are having higher values of displacement compared to these two. Okay, so here you can see here for this corresponding figure, which is closer. Okay, this is the approximate what you called shape of the displacement that is obtained from a seismograph or maybe an accelerogram. On the other end, if it is more farther, you can see the distance between them is more farther. Okay, so depending upon this study, we come to know what is the location of the epicenter from our site. Okay, so a minimum of these are the velocities, okay, of P waves and S waves, depending upon the different properties of the Earth's crust or the upper lithosphere. Okay, where E is the Young's modulus, G is the shear modulus, rho is the mass density, and nu is the Poisson's ratio. These are not exact values. Okay, these are not constant values, but maybe slightly different variations are there depending upon where you are located. Okay, so if you are able to know the interval between the arrival of the P and S wave, if you are able to know the interval between the arrival of the P and S wave at a point of observation, okay, then we will be able to measure the the epicentral distance. How? Because you see, this is VP and VS. Okay, so TSP is actually the corresponding displacement. Delta PS. Delta P is actually the distance from the focus to the observation point. So delta PS by VS minus delta PS by VP. That is actually TSP. Okay, so the epicentral distance as such will be D is given as delta TPS divided by 1 by VS minus 1 by VP. Okay. So this is how we get these equations will be given in most textbooks. Okay, this is how we get identify the location of the epicenter, means the distance. So if you have a corresponding point here, okay, if you have a point, this is my site here. This is my site here, and I use this formula, and I obtain the value of D, the epicentral distance. So the value of D will be somewhere around, this is the distance D. It will be a circle anywhere around this place. It may be a focus or epicenter. Okay, somewhere around this circle, it will be the focus or epicenter. So if you are able to get the corresponding readings from 3 different stations, okay, if you are able to get the corresponding reading from 3 different stations, the intersection of the corresponding value of the radius of each of these circles will help you identify the exact epicenter of the earthquake. Will help you identify the exact epicenter of the earthquake. Okay, so you can see here once again I'm showing you here. Okay, by measuring the corresponding distance, you can see here, you see this corresponding figure, the distance between the if the distance is close, to the focus, the gap between P and S is very small. As the corresponding distance is greater, the corresponding gap between P and S is more greater. So depending upon that, we will be able to get the distance or the time interval between the arrival of the P wave and the S wave, from which we can calculate the epicentral distance, which is actually a circle, okay, of radius d. So if you have if you are able to get the corresponding measurement from three different seismic instruments, they are located in different parts of the country or the continent, then depending upon that, we'll be able to locate the exact epicenter of the earthquake. Okay. So this is the last topic in this. This will wind it up. What are the different classifications of earthquakes? Okay. What are the different classifications of earthquake? I told you one is interplate and intraplate. Interplate is actually that occurs at the plate boundaries due to the convergent, divergent, and transform plate boundaries. Intraplate due to the different slips and faults. Okay. So slip is actually the slip that has occurred. It actually occurs at the fault itself. Okay. So the slip and strike, dip slip. There are two types of slips: dip slip and strike slip. Okay, so depending upon this dip slip and strike slip, you can classify the corresponding earthquake as either interplate or intraplate. And depending upon the focal depth, okay, if it is less than 70 kilometers, I told you most earthquakes are most dangerous. It is shallow, with less than 70 kilometers. So most of the earthquakes are shallow. Okay, it's called shallow depth earthquakes. Then intermediate between 70 and 300. And if it is greater than 300, it is called a deep earthquake. Deep earthquake only occur at subduction zones. That is when one corresponding plate goes below the other plate. Okay, there may be volcanic activity as well as earthquake that occurs. Maybe volcanic activity and earthquake that occurs. So that will occur very deep down. Okay, since the entire crust is going very deep under the the crust. Okay, so as such, the deep earthquake occur only at subduction zones near the plate boundaries. And based upon the origin, okay, tectonic, okay, which also includes the faults due to faults, okay, then volcanic due to volcanoes, microseism is something like due to natural effects. Okay, due to natural effects, some disturbances will be caused, okay, which will result in an earthquake. And then due to explosion, construction, reservoir, mining, etc., all these will also result in earthquake. Mining areas are dangerous. Even an explosion occurs. Usually in mining, we use explosives. So in that case also, small earthquakes, not very large earthquakes, but small earthquakes can be developed. And then depending upon the epicentral distances, local less than 1 degree, 110 degree, which is regional, and teleseismic, if it is greater than 10 degree, depending upon the angle of how the seismic waves reach. And then depending upon the magnitude is a measurement of earthquake. Okay, how much energy is being released. Depending upon that, a scale has been developed. So depending upon the magnitude, minor, light, moderate, strong, major, and great. You must have seen in newspapers that Japan got an earthquake of Richter scale, some value, Richter scale 7 or 7.9, or etc. These are magnitudes of the earthquake. And I think one last topic, and then we'll wind it up. Now, as I told you, earthquake occurrence. I told you earlier that most of the earthquakes will occur at the plate boundaries, almost 80% of the earth. And there is one plate boundary, okay, which is also called the ring of fire, okay, where the maximum number of earthquakes and volcanoes occur. Okay, it is found in around the Pacific Ocean belt, Pacific plate. Okay, it's called a Great Earthquake Belt. Okay, around the Pacific plate as such, We call it the ring of fire, and most of the earthquakes and most of the volcanoes occur. I think I must have shown you this figure. You see, most the same figure. This is actually the Pacific plate here. Okay, so most of the earthquakes, even in other areas, there are earthquakes, but it is comparatively less. But in this area, okay, the largest number of earthquakes and volcanoes occur, and hence this corresponding area is called the ring of fire. Okay, around the Pacific plate, maximum earthquakes and maximum destructions occurs in this area. You may ask why Japan is having too much earthquake or Indonesia is having too much earthquake. It comes all around this region. Okay, Japan, Indonesia, all these areas. So almost you see a great part. I think I know result. Yeah, about 81% of the Earth's largest earthquakes. Hence, if you classify, if you take only the largest earthquakes, maybe above Richter scale 7 point above six. If you take almost 80% of that will be around this ring of fire, and the rest 15% will be around the Mediterranean Asian belt. Means when the Eurasian plate, I think, yeah, when the Eurasian plate and this corresponding area, 15% of the earthquakes occur in this area, and in the Indian plate run into the Eurasian plate. This is the Indian plate or Indo-Australian plate, and this is the Eurasian plate here. Okay, here there is an area of earthquake, almost 15% of all the greater major earthquakes. Okay, I'm not talking of all earthquakes, but of the major earthquakes. Then 5% occur in the interior of the plates. Okay, these are called they're in between the plates also. You may find earthquakes. You can see here small earthquakes in between the plate. Okay. So as such, the 5% occurs near the interior of the plates and or at the ridge centers. Okay. So as such, this is how earthquakes occurrences is there. Now, how much earthquakes? What is the frequency, or how long? How does it take? Means what is the difference in time between two different earthquakes? Okay. So here a table has been given to you, which is actually a table from NEIC, which has given you the number of earthquakes, an average number of earthquakes that occur depending upon the magnitude. Okay, so very minor earthquakes means of having magnitude less than 3 occurs almost 1000 per day. Okay, 1000 per day, and great earthquakes that is greater than 8 occurs one every year. Okay, one every year. Most of the earthquakes as such are very small, and hence we will never feel it. If it is less than 3, we will never feel it. Only very well tuned seismic instruments will be able to capture those values properly. Okay, so this is actually the frequency. Okay, you can see the number of earthquakes avoid. Okay, that has occurred. So as the magnitude increases, the number of earthquakes decreases per year. So the different major earthquakes in the past, especially that has been caused, that has been indicated here. Okay, it is giving an example here. So with this, we will wind up our session here. So we had covered two topics today. One is regarding the interior of the earth, the seismological aspects, and the second, the basics of earthquake. What are the basic principles of basic terms regarding earthquake, how the different types of seismic waves, and then finally the frequency as well as the occurrence. So if you have any doubt, you can come up. Otherwise, we will wind the session up.
Sir, good afternoon, sir. I'm Aarti.
Bata.
Sir, I had a question that in the S waves and P waves that we are having during this earthquakes, so these waves occur first or the surface waves? I mean, which waves are recorded first while testing, while we
P
want to
waves,
know
P
the.
waves, P waves will come first. They are the have highest. You see, P waves will have a what called speed of 4 to 7 kilometers per second. Okay, per second, 4 to 7, approximately. That is the that. And if you come to S waves, 3 kilometers per second is the average speed. It also depends upon the material, okay, the medium through which it travels, but average 3 kilometers per second is what S waves. And surface waves are much more slower. Okay,
Okay. So then the seismic devices which are being recorded, they record these P and S waves.
all PS as well as means body waves will record P and S as well as surface waves will record.
Okay. Okay. Thank you, sir.
We can. I think it's responding here. You can see. So the first P waves will come, so that will be recorded. Then S waves will come, and then surface waves will come. Surface waves will be more having more displacement, and as such they will be having greater value of displacement and the greater value of acceleration.
Okay, sir. Thank you.
Any more?
Sir, by velocity we will distinguish between P waves and S waves.
Not by velocity. How can at a site which comes first? That will be the P waves. So it'll come in
Okay, sir.
disturbance. It will come first. A few displacements will show indicator that's a P waves. Then after a small instant of time, another few thing will come. That will be S waves. Then after a small interval of time, then the original actual heavy waves will come. Means actually that occurs. P and S waves are something that gets recorded by the seismic instruments as such. So it does not it causes damage, but not that much damage. The surface wave will cause maximum damage. So its displacements and acceleration will be very large.
Okay, sir.
We'll come to how to measure this. Means what are the instruments used in measurement of earthquakes in the next class.
Okay, sir. Thank you.
Any more doubts as such? There is something which I had missed out. That is regarding slip. Okay, you see, actually, the normal fault and reverse fault that will result in dip slip, and the let me show you the figure. Yeah, the normal faults and the reverse faults as such, this inclined way in which the fault moves, okay, we call it the dip slip. Okay, one hanging wall and foot wall are moving relative to one another in the up and down direction. Okay, if they are moving sideways like in strike fault, we call this one as strike slip. The slip, that means the movement, the how far it has been moved, that is called a slip. Okay, how far, I think the technical term is given in okay, dip slip, it is here, the dip slip. Okay, this is dip slip, and strike slip, it is not given here. Strike slip is along this direction. Okay, this dip slip along this direction, strike slip is along this direction.
Sir, heave and throw direction, sir, in this case, sir.
What?
Which is horizontal and which is vertical, sir?
This is vertical.
Heave and throw, sir.
Even throw, heave is horizontal.
Okay, sir.
Throw is vertical. So you can see here, if it moves, if this corresponding block moves right, corresponding block moves this type, the corresponding movement along this direction is called slip. How much it has slipped.
Okay,
Okay,
sir.
this is called strike slip. You can see here the strike vector. Okay, if it moves along this direction, okay, it slips. Either one is moving upward, the other is moving downwards. That is called dip. Okay, we call it dip vector.
Okay, sir.
Anything more? You can see here. You can see here in this figure, large number of black and red are mentioned here. This is actually the Pacific Rim here, the Ring of Fire. Okay, if there are no more questions, and then we'll wind it up. There is one thing which I think I have given a mistake by mistake. I told you that the P waves, as the P waves and S waves will what do you call it, reach the surface of the Earth, and a part of that will get transformed to surface waves. Surface waves are more dangerous. They are slow moving, but they are more dangerous. Okay, so as such, we when I design structures, okay, as such, we'll be more concentrated on the corresponding magnitude or the displacement or the acceleration of the surface waves rather than the P or S. Okay. I think I had a table somewhere here. I think I had missed that table. Okay, to keep in the figure here. Go to that any standard, this one you will get this one. Figures you will get anywhere. Okay, let me tell you once again, P waves will travel through both solids. Let me show that figure. Yeah, P waves will travel through all three: solids, liquids, and gases. Okay. P waves will travel through all these things. It's like a normal what you call sound waves, how they travel. That's why it's also called a compressional waves. Okay, compressional waves. Sound waves are like that. Sound waves travels like that. And then S waves also. S waves, as I told you, there are two horizontal directions, horizontal, vertical. So depending upon that, they may be called as SH or SV. Okay, SH waves and SV waves. That is also used. This S waves as such can travel only through solids. Okay, can travel only in solids. S waves is actually what? Shear waves. Shear waves can travel only through solids. Liquid as such has no shear. Okay, so they cannot travel through liquids. They can travel only through solids. I think I deleted that one.